As we've seen, obtaining a solution to a large linear system can get tedious, and therefore we used augmented matrices to do that. But in general, a matrix is a rectangular array of elements. So for example, we stored the coefficients of a linear system in the matrix, and these numbers are called the entries in the matrix. Now the size of the matrix is the number of rows, which is P in this case, by the number of columns being Q. So each row of this matrix represents the constants in each linear equation that we see. Now vectors, on the other hand, are special types of matrices with either one row or one column. So for example, a column vector here has multiple rows and one column, whereas this row vector has multiple columns and one row. And we'll see that when we multiply this matrix of coefficients by this column vector, we're going to get these equations. And the column vector on the right hand side represents these constants on the right. Now we can also use compact notation to represent matrices. So in the first notation, where we need to know the size of the matrix, we have the matrix C with entries in row I and column J, and we can write the number of rows by the number of columns here. And here we have the entries in row I and column J for matrix C. And here is another compact representation for our matrix C with entries in row I and column J. Now a square matrix, for example here, where we have the number of rows being equal to the number of columns, is a special type of matrix which we'll look at further later on. So this type of matrix has the following elements on the diagonal. So the entry in row 1, column 1, the entry in row 2, column 2, and the entry in row 3, column 3. And by inverting a matrix, we can solve systems with many unknown variables.